This video is on lessons 4.12 and 4.13. 4.12 is a continuation of our log discussion, but we are going to be talking about the number e. You may have noticed this number or this button on your calculator, and it is also, like pi, irrational, okay, which means it goes on forever. There's no rhyme or reason to the decimal pattern. It goes on forever with no pattern. So it is approximately 2.72. And its main use, especially in this course, is used in exponential modeling. So let's look at an example where we're going to end up using E in our formula. Exercise 2. A population of llamas on a tropical island can be modeled by the following equation. P equals 500 times E to the 0.035 t, where t represents the number of years since the llamas were first introduced to the island. So part A asks how many llamas were initially introduced at t equals 0. So the starting population, the time would be 0 years. So you're going to plug in 0 for t. So that's 500 times e to the 0.035 times 0. Well, anything times 0 is 0, so that's p equals 500 times e to the 0. And back from your exponent rules, you know that anything raised to the 0 power is 1. So this turns out to be 500 times 1, which is 500. So that means, according to this formula, this tropical island started with 500 llamas. Then it says, algebraically determine the number of years for the population to reach 600. So we want to know how many years, which is our t, will it take to get to 600. So we're going to plug in 600 for our population. We want to know our population will be 600. How many years will that take? So we are going to start by getting t alone. You will notice t is in an exponent spot. So we're going to have to use logs to bring it down eventually. But first, let's get rid of anything we can that is not directly attached to the t by moving it to the other side. So we can divide this 500 over. Well, when you divide 600 by 500, I'm going to leave it as a fraction, but I'm going to reduce it. It is 6/5. So we get 6/5 equals e to the 0.035 t. Now, I've moved everything over that I can. So I'm going to have to log both sides to get the exponent to drop down. So I'm kind of running out of room here. I'm going to move over this way. So I'm going to have the log of 6/5 equals the log of e to the 0.035 t. And now that I logged both sides, I can drop this exponent down to in front. So I'm going to have the log of 6/5 equals 0.035 t times the log of e. Now, we're going to definitely need a calculator because we're going to divide the log of e to the other side. And then I'm going to divide the 0.035 to the other side. So you end up getting a final answer. So you would type all this in your calculator. I'm running out of room, so I'm not going to show all of those numbers. But you would type log of 6/5, close your parentheses, divided by the log of e. By the way, if it asks you for an exponent to put in for e, if there is no exponent, remember it's an imaginary one, so you might have to type log of e to the first. And then get an answer and then divide over the 0.035. It turns out to the nearest tenth of a year to be 5.2. So now we're going to talk about the natural log, which you need to know because you're going to use e a lot in word problems. It's inverse. Remember, inverse means opposite. So the opposite of e is the natural log. And the abbreviation for the natural log is ln. You'll notice it on your calculator. It is just ln. There is no base. You don't have to worry about any bases. You're only going to use the natural log if you're working with e. Now remember, opposite mean it it will undo e. So the opposite of multiplying is dividing. The opposite of adding is subtracting. The opposite of squaring is square rooting. The opposite of cubing is cube rooting. The opposite of e is the natural log. So you just have to know that to get e to go away, because we don't really like to work with e. We want it to go away so that we can bring the exponent down. So to get rid of e from one side of an equation, you're going to natural log both sides, and that'll get e to cancel out. So let's do an example. Exercise 5. You have a hot liquid cooling in a room, and we're going to be using this example in the next lesson, so make sure you're familiar with this example. A hot liquid is cooling in a room whose temperature is constant. Its temperature can be modeled using the exponential function below. So this equation represents the temperature after m is in minutes. So after a certain number of minutes have gone by, you can figure out the liquid's temperature using this formula. So part A, what was the initial temperature of the water at m equals 0? Do it without a calculator. So initial is starting, so at the starting temperature would be no minutes have gone by. So you're just plugging in 0 for m. Well, I should put a 0 there. 101 times e. Well, if I plug in 0 for m, 0 times anything is 0 plus 67. You know that e to the 0 or anything to the 0 is 1. Whoops, hold on, let me erase that because I can't just write over that. 101 times, this turns into 1 plus 67. If you follow your PEMDAS, 101 times 1 is 101, plus 67 is 168. So the starting temperature of my liquid was 168. How do you interpret this statement? T of 60 equals 83.7. Well, you will recall, if you're in the parentheses, you're the input, and the input in this case is your m, so that is your minutes, and the number on the other side of the equal sign is your output, and what you are actually finding is the temperature. So what this data point says is that after 60 minutes have gone by, the temperature will be 83.7 degrees Fahrenheit. Part C, using the natural logarithm, determine algebraically when the temperature of the liquid will reach 100. So I know what the temperature will be. So I'm not plugging that in for m. It's not a minute, it's a degree. So I want to know when will I get to 100 degrees. So I'm plugging in 100 for the left side of the equal sign for T of m. So that's 100 equals 101 e to the negative 0.03 m plus 67. So you're going to solve for m. So the first thing you always move over away from m is anything that's added or subtracted. So I'm going to subtract the 67 over to the other side. So 100 minus 67, that gives me 33 equals 101 e to the negative 0.03 m. Now I have to get rid of the 101 out in front because it's multiplied with the e, which is attached to the m. So I'm going to divide the 101 over to the other side. And I am going to leave it as a fraction. I'm just going to leave it as 33 over 101. I'm going to move down here to do my work down here because I ran out of room. So I have 33 over 101 equals e to the negative 0.03 m. Now, this is the important part. This is where it gets a little different. You could use logs. You could log both sides so that the exponent drops down, then divide by the log of e, then divide by negative 0.03. That's fine. But it's actually a little quicker to do this. Because e's inverse is the natural log, if I natural log both sides, so I'm going to ln both sides, the natural log and e cancel each other out. So these go away kind of, and you're left with negative 0.03 m on the other side. Now this will be a number. You're going to use your calculator to see what the natural log of 33 over 101 is. But before I do that, I'm just going to show that I'm actually going to end up now dividing by negative 0.03 to get m alone. So now I'm going to type in this whole thing into my calculator, and you got to make sure that you type it in correctly. So first do the top. Type in the natural log of 33 divided by 101. Hit enter, get a number. Then divide that by negative 0.03. You're going to turn out to get 37.3 minutes. So when you're working with e and you need the exponent to drop down, you just natural log both sides, and the natural log and the e kind of cancel each other out. Okay, so for part D, it says on average how many degrees are lost per minute over the following interval from 10 to 30. This is otherwise known as average rate of change from 10 to 30. So if you recall, average rate of change, you're subtracting your outputs on top, that's a y, y2 minus y1 over x2 minus x1. Well, you know the difference in the x's because they told you from 10 to 30. So you're going to do 30 minus 10 on the bottom. You need 30 and 10's outputs. So all you have to do is plug in 30 and 10 into your equation for m, or you could graph it and look at the table. Well, 30's output is 108.1 minus 10's output is 141.8. When you subtract those, on the top, when you divide it, subtract and divide it out, you're going to get a negative 1.7. So what that means, the negative means it is decreasing. So it is decreasing 1.7 degrees every minute because we are measuring in degrees per minute. So there you go. That's it for lesson 4.12. So you needed to learn that the inverse of the number e is the natural log. So you're going to natural log both sides if you need to get the exponent to drop down from an e, only from an e. So you're only using this if you're working with e. So on to lesson 4.13. 4.13 is also going to work with e. So if you start following along in the first paragraph, in the worlds of investment and debt, interest is added onto a principal. Your principal, again, is your starting amount. It is added onto your principal in what is known as compound interest. The percent rate is typically given on a yearly basis, but it could be applied more than once a year. This is known as the compounding frequency. So frequency is how many times something happens. So if you want to make a note to yourself, frequency is how many times something happens. So it depends on what that something is that you're doing in the problem. So we're going to take a look at a typical problem to understand how the compounding frequency changes how interest is applied. So exercise 1, a person invests, so they start off with $500 in an account that earns a nominal yearly interest rate. And again, as soon as you see percents, you should convert them to the decimal equivalent. 4% is otherwise known as 0.04. To do that, you just either move the decimal 2 spots or divide it by 100. How much would this investment be worth in 10 years if the compounding frequency was once per year? So you've done this before. You start with your initial investment. You multiply it by, you're getting an additional 4%. You're not getting only 4% of your money. You're actually getting 104% because you're keeping what you have plus adding on 4%. So that's 1.04, remember your 1 plus r, to the t, which this case we're doing 10 years. So if you type that out on your calculator, you're going to make $740, or you're going to have, not make, and 12 cents. So you made $240.12. If, on the other hand, the interest was applied 4 times per year, 4 times is known as quarterly compounding, why would it not make sense to multiply by 1.04 each quarter? So that would not make sense because you would be increasing by more than 4% a year. Because you'd be increasing 4% for the first 3 months, and then another 4%, and then another 4%, and another 4%. Than 4% in a year, which is way more than you were supposed to get. You were only supposed to get 4% a year if it's done more than 4 times, or if it's done 4 times a year. So the pattern is fairly straightforward. For a shorter compounding period, we get to apply the interest rate more often, but at a lower rate. So exercise 2, how much would $1,000 invested at a nominal 2% yearly rate, but it's compounded monthly, be worth in 20 years? So we are starting off with our $1,000. In the parentheses, remember, is 1 plus your rate. Now here's the issue. First of all, 2% is 0.02. You're not going to add on 0.02 because we are actually compounding it monthly. So you have to add on 0.02 divided by, it's not in 1 year, it's in 1 month, and there are 12 months in a year. So you're going to divide it by 12. And then up here, our time is for 20 years, but since you're doing it monthly, you have to multiply that by 12 months in 1 year. So now again, you would type this all into your calculator. Just be careful that you type it in correctly. Make sure that these are in your exponent spot. Make sure you close your parentheses. You should get, and you should practice typing it in so you know if you got this right. If you're typing it in right, it's $1,491.33, which is choice 2. So we can simplify this into a formula. It is known as the principal amount times 1 plus the rate divided by how many times you're compounding a year, which they refer to as n, raised to the n times t. So if you're compounding this more than just once a year, you need to use this formula. So this is if you are compounding more than once a year. If you're just doing once a year, you can use our 1 plus r to the t. But if you're doing more than once a year, you need to use this formula. Okay? So moving on, if we are continuously compounding, so what this means is you are literally compounding your interest at every moment in time. Every second that goes by, you are earning interest. Every millisecond that goes by, you are earning interest. So it is not being compounded monthly, daily, yearly. It is continuously being compounded. So I could tell you how much you make after every second of your life that goes by, or even smaller. So to do that, we have to use E. So this is where E is going to come into place. You need to know this formula if they talk about compounding continuously. So here is an example of when that's going to happen. And you will see the words continuously compounded in the question. So it says we're starting with $350 and our rate is 2%, so that's 0.02. And it is being continuously compounded. As soon as you see that phrase in your question, you should be thinking, I'm going to have to use, and this is what I call this formula, it's the PERT formula. P times E to the RT, PERT. So you're using PERT if it's continuously compounded. So first they want us to just write the equation. So the equation would be A of t, which is how much you're going to have, equals our principal amount was $350. E is E, you can't change E. The rate is 0.02, and it said after t years. So I just leave t as t. Now it's for part B, it says how much would you actually get after 20 years? You're just going to plug in 20 for your time. So you would get 350 times E to the 0.02 times 20. And again, just from here, use your calculator, just type that all in. You would get $522.14. And that should make sense that it's not that much because you're only getting 2% every second or every whatever. It's continuously being compounded, but you're getting only 2%. So that's not a huge percentage. So that is it for lesson 4.13.